Hello everyone, welcome to this lesson. So in this lesson we're going to go through 5 examples of ordinary differential equations, and we're going to solve them using the 6 methods that we have discussed thus far. The Euler's method, the Hans's method, midpoint Ralston, the third order Ronch-Kuda, and also finally the fourth order Ronch-Kuda. Now I have created a notebook here that houses all of the 6 methods, and with this notebook all you need to do is actually change 3 different things here, and you can evaluate any differential equation using all 6 methodologies. So let's actually see what are the changes. So the changes, of course, is going to be the function, the ordinary differential equation, and also you can add here the exact solution if you have it available. Here you would define the integration limits, and also the step size, and also here we calculate n. And the third and final change that you're going to be doing is also defining the initial condition for each one of the codes. And the reason that is because we want to replace the x and y values for the previous code. So actually, let's begin. So the first ordinary differential equation I'm going to be dealing with here is x multiplied by the square root of y. So what I'm going to do is I'm going to take this ordinary differential equation and its exact solution, and I'm going to put it here. And here we're dealing from integration limit 2 to 7, which I have here, 2 to 7. Let's actually do a step size of 0.5, and the n is going to be calculated. So here, Euler, the initial condition for this particular problem is 2 and 4. So x equal 2, y equal 4. So actually, let's run here the packages. And also I'm going to run this specific function, get the integration limits and the number of calculations, and let's actually run Euler. Okay, perfect. So you can see 2 to 7, increments of 0.5. Here we have the approximation of Euler, the true values. And you can see, as you have seen with previous lessons, it captures the trend, but still a little bit of error. Now we can reduce this error by reducing the step size, but in this case we're going to keep the step size 0.5 to see how all of them are going to fare. So again, here initialization, we're going to be, the only thing we're going to be changing with each code is the initial condition. So it's going to be 2 and 4. So let's see, let's run the Hans. Excellent, much better improvement over the Euler's method here. Let's actually do the midpoint. I'll change the y here to 4, so you have 2 and 4. The midpoint should give us similar results to the Hans, because again they're both second order Ronch-Kuda, and the Ralston here should give us again a similar one. So 3. So let's actually go through the third order. Should be a slight improvement. You can see here, and also the final, which should be the best of all of them, the fourth order. And you can see it's almost identical to the true value, and you can see this from the values here: 175.55, 175.56, 133.68, 133.69. So very close numbers, almost identical. So let's actually go to the second example. And second example actually we did before. The only reason I'm going through it again here is because we never applied the Euler's method to it. And this is the sine x squared multiplied by y. So let's actually take these two and put them here. The integration limits here is 0 to 5, as you remember. 0 to 5. Let's actually still deal with 0.5. And the initial condition was 0 and 2. So I will run the function, run the new integration limits and number of calculations, and let's see Euler or Euler's. So you can see captures the trend, but still we have a lot of errors, you can see here. And you can, in this example, you can see the limitation of linear extrapolation. Here there wasn't a lot of curvature, so the approximation was good, but as the curvature increased, especially here, you can see we incurred a lot of error. So let's actually see the Hans, which should be a really good improvement on this here, and the midpoint as well. And the Ralston should be the same as the last two. And the third should be a slight improvement over the last 3 methods, as you can see. And this should be the best improvement of them all, as you can see from the numbers: 27.87, 27.91. So this is, again, by far the most superior, and it's not a surprise because we're using 4 different derivatives to describe the derivative in each interval. So let's actually go to the third example here, which is 2 multiplied by y, and let's take the exact solution. We're dealing with an integration interval 0 and 1, and here y is equal to 1, x is equal to 0. So I'll add this here. It's 0 and 1. Maybe because it's a small integration, let's actually do this to 0.2. And x and y is 0 and 1. So let's run the function, run the integration limits, and run the Euler. Good. Again, captures the trend, but still we have error. Let's see what the Hans is going to do. Much better approximation. This should be similar. Also, Ralston should be similar. And this should be a slight improvement on the last 3. As you can see, slight improvement. And this should be by far the best of them all. And let's go to the fourth example, which is x times y. Again, here is the exact solution: exponential x squared divided by 2. We're dealing with an integration interval 0 and 2, and the initial condition is the same as the last one. So I'll put this here. We're dealing with integration interval 0 and 2. Now we're dealing with the same initial condition, so I'm just going to run this. All right, great, capture the trend, but as we see with a lot of them, we have incurred, we still have a lot of error here. Let's actually run the Hans. Excellent improvement. Midpoint should be similar. Ralston should be similar. Should be slight improvement. And finally, the best of them all. As you can see, it's almost identical. Let's go to the last and final example for this lesson. And this is going to be y plus 3 with an exact solution of exponential x minus 2 minus 3. So I'll take these. I'm going to paste them here. Here the integration interval is 2 to 4. And the initial condition here is -2 and 2. And I'm going to keep the step size as 0.2. You can actually play with this however you would like. So I'm going to run the function. I'm going to run the integration limits. And here at x equal 2, y is -2. I'll run this. Okay, great. 2 -2 should be a really great improvement over this. As you can see, 2 -2. Similar as the Hans. Here, 2 -2. Again, you can see very, very similar. This should give us just a slight improvement. 2 -2, as you can see. And this should give us the best improvement of them all. All right, perfect. So as you can see in this lesson, we have introduced 5 different ordinary differential equations with their integration limits and their initial condition. You can play around with the integration limits, and also you can play around with the step size. As you can see, these techniques are very simple. They just depend on extrapolation, and with each one of the Ron-Shkuda, this started with linear extrapolation. Then we went to the Hans, midpoint, and Ralston, which added 2 derivatives to describe each one of these intervals. And also with the third, it gave us 3 derivatives, and we saw it was a slight improvement. And with this series, we introduced the 4th order, which is the most common type used for solving ordinary differential equations, and he used 4 different derivatives, and you can see its massive superiority over all of them. So that will be it for this series for ordinary differential equations. I hope you have found it to be very, very simple and also very effective and also powerful techniques. And this is the great thing about these techniques, or numerical methods techniques, is that they're very simple, they're very effective, which makes them very, very powerful techniques. to solve numerical or mathematical problems. So thank you very much, and I will see you in the next series.